Okay, so what we're going to be doing today is essentially showing that the area under the t-distribution curve is equal to 1 for all integer positive values of the degrees of freedom. So let's start by writing down the PDF of the t-distribution. It looks quite nasty if you've never done it before, but using some special techniques in complex analysis, it shouldn't be too hard. Let's start off by integrating this from negative infinity to infinity. And the first thing we can do is bring this part here outside of the integral, because this is just a constant. And we can also do a substitution, t over root v. So let's do both of those in the same step. Let z equal t over root v. So this implies that root v dz is equal to dt. So let's transform this integral. We get the gamma of v plus 1 over 2 over root pi nu gamma nu plus 1 over 2, and then we integrate root v. Let's write this instead as root v dz over 1 plus z squared to the 1 plus v over 2. Oops. So what we can do now is cancel the root v with the v here to get gamma of v plus 1 over 2 over root pi gamma of v over 2. Then we integrate this from negative infinity to infinity, and what we can do is factor the bottom out as z minus I, z plus I, and then we can write 1 over one of the factors to the power of 1 plus v over 2, and divide the whole thing by the other factor to the 1 plus v over 2. So I'll show you what I'm doing there now. Z minus I I'm going to write this as the positive factor and this as the negative factor, and I'll show you why in a minute. So at this point it might look like this is a really hard integral to evaluate, but actually it's not so bad if you use a bit of complex analysis and the residue theorem. Let's start by drawing a complex plane, and let's draw a semicircle starting at minus r to r. So this section is obviously, if we take the limit going to infinity, we're going to get the original integral. But let's draw a semicircular arc and call the whole contour C. Let's call this semicircular arc gamma, and let's call this part here I. Notice that the contour integral over C is just equal to the integral from minus r to r plus the integral over gamma. Now if we analyse gamma, we'll see that the integral over gamma of 1 over 1 plus z squared to the nu plus 1 over 2 dz, we can use the estimation lemma, right? We can either use the reverse triangle inequality, or we can, you know, do a substitution. Either way, you're going to see that this is essentially the limit as r goes to infinity of pi r over r squared minus 1 to the nu plus 1 over 2. And as long as nu is greater than or equal to 1, this is obviously going to converge to 0. So we've shown that this goes to 0 when we take r going to infinity. So we've essentially just proven that the contour integral over c is exactly equal to the integral from negative infinity to infinity. So we can go back up and replace this integral sign with the contour integral sign. Okay, so at this point, evaluating this isn't too hard. We can use Cauchy's differentiation formula, which says that 2 pi I over gamma of n times a function to the nth power evaluated at a is exactly equal to, sorry, I think this should be n minus 1 evaluated at a is exactly equal to the contour integral over c of f of z dz over z minus a to the n. So we can use this differentiation formula and we get gamma of nu plus 1 over 2 over root pi gamma of nu over 2 times 2 pi I over gamma, and because the power is nu plus 1 over 2, you get nu plus 1 over 2 times the derivative, the v plus 1 over 2 minus 1th derivative with respect to x, sorry, with respect to z, of z minus, sorry, z plus I, because this is the arith of z here, to the minus v plus 1 over 2. This is evaluated at z equals I. So this might look quite nasty, but there's a nice formula that we could use for this, which says that the k minus 1th derivative of x to the minus k is exactly gamma of 2k minus 1 times negative 1 to the k minus 1 x to the 1 minus 2k all over gamma of k. So we can actually just use this where x is z plus I, or we could even do this little bit of algebra here. This simplifies to 2 pi, sorry, we got the root pi and the pi on top, so we can write this as 2 root pi I over gamma of nu over 2, because these two factors cancel, times by, in this case we have k is equal to nu plus 1 over 2, which implies that 2k minus 1 is equal to nu exactly. So this is equal to, sorry, this part here on top is equal to gamma of nu minus 1 to the nu over 2 minus a half, and then x to the minus nu over gamma of nu plus 1 over 2. And we evaluate this at x is equal to 2i. So this isn't too bad. We can just plug things in now and start cancelling some stuff. Notice that v over 2 minus 1 to the I is that's just I to the v. So 2 root pi I gamma of v I to the nu I to the minus 1 because we've got minus 1 to the pair of minus a half over gamma nu over 2 gamma nu over 2 plus 1 half, and then we have 2i to the v. So we can cancel some stuff out pretty simply. If we cancel the I to the v terms, this becomes entirely real. Now we can use a formula called Legendre duplication formula, and this says that gamma of x times gamma of x plus 1 half is equal to 2 to the 1 minus 2x root pi gamma of 2x. If we use this formula, we can see that we have something similar on the bottom, except that x equals v over 2. Either way, we can substitute this in. We get that gamma of v over 2 gamma of v over 2 plus 1 half is 2 to the 1 minus nu root pi gamma of 2 nu over 2 is just nu. And if we substitute this into the result, we get 2 root pi gamma of nu over 2 to the 1 minus v root pi gamma of v or nu 2 to the nu. And if we do some cancelling, you can clearly see that this equals exactly 1. That's such a nice cancellation there. So essentially what we've proven here, with use of complex analysis and a few formulae for the gamma function, we've proven that the t distribution curve for any positive integer parameter is going to have an area of 1. Let's write this out in full. I hope this was helpful. I hope you enjoyed it. It took me around 5 hours to prove this. I originally proved it for the case when nu equals odd, which is somewhat easier, but here this is just the general case proven. Yeah, I really hope this was helpful. I hope you took some enjoyment out of it. I know that I certainly enjoyed deriving this. It was a real challenge. Yeah, stay tuned for more.